The final concept that we cover in this first part is the concept of intensity, or the average intensity of a point process. So this concept is very similar to the notion of a mean of a distribution. It's the first moment, as it's called, of a point pattern distribution. And essentially, it is a measure of density. You can consider it rescale density, where you measure the number of points per unit area. So if you have a square mile and you have 5 events per that square mile, the intensity will be 5 per 1 square mile. So the intensity depends on the units of measurement, of course. It's always per area. And in practice, this can be a little bit confusing because it has to do with the projection that you use for your particular map. And so this projection will determine whether your distance units are feet or meters or things of that nature. Now, a very important aspect of the measure of intensity is you basically count all the points in a given area, but the question is, what is the relevant area? And the relevant area is determined by what we call a bounding polygon. And in classical point pattern analysis, the bounding polygon was often rescaled so that it became a unit square, a square with 1 unit distance on each side. And this is somewhat unrealistic, but in many textbooks examples, it is still the way that the point patterns are represented. Now, with the advent of GIS, we can, of course, do much better than that, and we can use the actual boundary, the actual regional boundary from the GIS, or we can use a bounding box, which is a rectangle, or a convex hull, which fits around the points as tightly as possible. And I'll now illustrate these in turn. So we start with the bounding polygon, which is basically extracted as the boundary file from the GIS. In this case, the same example we will be using throughout. The location of supermarkets in the city of Chicago, the black line represents the city of Chicago boundary. So then the intensity would be computed by dividing the number of points, 149 to be precise, by the area included in the boundary of the city of Chicago. A more regular shape is the bounding box, which is actually a rectangle constructed around a point pattern by taking the smallest value in the x-coordinate, the horizontal coordinate, and the largest value in the vertical coordinate, or the y-coordinate, as the upper right corner of the box, and then the largest value along the x dimension, or the horizontal dimension, and the smallest value along the vertical dimension as the lower left corner of the box. And in our example for Chicago, this looks something like this. So you see clearly how the upper right corner, the upper left corner rather, is constructed by taking the x-coordinate of the leftmost point and the y-coordinate of the highest point. And similarly, the lower right corner is constructed by taking the y-coordinate of the rightmost point, the y-coordinate of the lowest point, more precisely, and the x-coordinate of the rightmost point. So this creates the bounding box, and so now the measure of average intensity would be 149 divided by the area within the rectangle. And then a third option is the convex hull, which is a polygon that fits around the points in the tightest possible fashion. If you recall the bounding box, there's a lot of white space in here, especially in the lower right and the upper left of the point pattern. In a convex hull, this is not the case. The convex hull basically encloses the points. You can, if you think of the points as little pegs sticking out, then if you take a rubber band and fit it around the little pegs, the convex hull is the tightest fit. And there are several ways of doing this mathematically, but basically it looks something like this, where you see that the polygon connects all the outermost points of the point pattern. And so then again, the average intensity in this case would be the ratio of 149 by the area in the convex hull. In the literature, there have been a number of adjustments where, in essence, the bounding box or the convex hull are scaled out just a little bit. In a number of software packages, this is implemented and referred to as the Ripley-Rasson transformation. And essentially, it's a rescaling, which is a fraction of the number of points, and moves the boundary out just a little bit. And we won't really get too much into that. But it's important to keep in mind that all this, of course, affects the denominator in the calculation of the average intensity. The numerator remains the same. There are always 149 points, but the area changes. And just for comparison purposes, I computed this for the Chicago example. So we have 149 points. If we take the GIS boundary, the intensity is 2.31. And the units are kind of weird because the projection is in feet. So the actual numbers are 2.31 times 10 to the minus 8. So more importantly, you can see the difference here where the tightest fit was the convex hull. And for the convex hull, the intensity is 2.53. Then for the adjusted convex hull, so that is just moved the hull just out by a little bit, we see that the intensity goes down a bit to 2.34 and is very close actually to what we get for the GIS boundary, 2.31. And then the worst cases, the lowest intensity, we find for the areas with a lot of white space. So if we take the tight bounding box, we get 1.55, and if we get the adjusted bounding box adjusted out, meaning there's even more area, we get the lowest value of 1.51. So the moral of the story is that the intensity estimate does not only depend on the number of points, which is the numerator, but critically also depends on how the denominator, the area, is conceptualized or is defined. And this is where we're going to end the first part of our second module.